Today we are going to talk about 1.5. So 1.5 is this idea of differentiability and continuity. And so you have already read the book. So differentiability, that's a big, nice word. Go impress some people with that. Differentiable or differentiation, those are good ones too. So differentiability and continuity. So remember from the book, I just want to do 2 examples. This will not be a super long one. Oh, unless I keep making mistakes. Or unless I just start talking, which about things that don't matter. All right, so let's talk about differentiability. That matters in this context of the course, and continuity. So the first example that I want to do, well, first off, let's remember, and you wrote this in your notes already, but for f, so continuous at x equals a. What does that mean for f to be continuous at x equals a? Then the limit, this means that the limit as x approaches a of f of x must equal f of a. So this right here, that x looks really weird, but this right here basically tells us 2 things: that f must exist at a, that the limit must exist, and that the actual limit must equal the function value. So I want to grab a picture from your homework, and let's use this as one of our examples here. So I'm just going to put it right about there, and we'll talk about this. So what I want to look at is, let's talk about if we're differentiable at some of these points, and if we're continuous. So let's look at, so determine if, and let's say that this is the function y equals f of x. I'll get a different color there. If f of x is continuous and differentiable at the following points, or at the given, not even points, at the given x values. Okay, so for the first one, sorry, my handwriting is a little bad there. For the first one, let's just look at x equals 0. Okay, so if I'm looking at x equals 0, again, what do we need to have here? 3 things here that we need to consider for continuity. Okay, and first off, the limit has to equal the function at that point. So that implies a couple of things. F exists at x equals a. The limit exists. Can I fit? There we go. And then the third one, which actually does kind of all of these together, the limit, which is the one we've already written, but I just want to write this down again, equals the actual function value, okay? All right, and you've looked at the examples, so you should feel pretty good about this. So let's look at 0 here. So if I look at x equals 0, so this is x equals 0. The first thing actually that I can see is that I'm not going to satisfy number 1. Excuse me. If I look at what is f of 0, so notice f of 0 does not exist. Thus, it is not continuous. And if it's not continuous, then it can't be differentiable. So if it's differentiable, then so there are a couple things there. If I know a function is differentiable, then it's continuous. Just because it's continuous does not necessarily mean it's differentiable, so be careful with that. But if it is differentiable, then it must be continuous. And so if I know if it's differentiable, it must be continuous, that means if it is not continuous, then it's not differentiable. And that kind of makes sense here, because what does it mean to be differentiable? It means I can draw one and only one tangent line at that point. So notice there's no function even there at 0 for me to draw a tangent line. I hope that kind of makes sense. Let's look at a couple other ones. Let's look at, I'm doing just a couple of, this is from your book, so I'm doing a couple of the suggested problems here, and I'm trying not to do do the ones that, that I'm giving you. So let's look at x equals -2. So if I'm looking at x equals -2, again, I'm going to look at, does my function exist there? Does the limit exist there? And the last thing, is the limit equal to the function value? So if we look at x equals -2, so I'm going to look here, x equals -2. So clearly, f exists at -2. I don't know if that's clear or not, but f of -2 would be this filled in point right here, and I could come over and I could figure out what that y value would be. So f exists at -2, so number 1 works, but look at number 2 here. If I look at the limit, what is the limit as x approaches -2? And in 1.4, you did limits. So as you notice, as I approach -2 from the left, I'm going to be at about 1. But as I approach -2 from the right, I'm not going to be at 1. I'm going to be at like 2. So remember, the limit says what's the general behavior of the function as we approach -2. Well, in this case, we can't tell. So this is not continuous. And I want you to be able to tell me why. Okay? So on the test or something, I would just say limit does not exist. And because it's not continuous, it's not differentiable. I can't draw, where would I draw the tangent line? Would I draw it here or would I draw it here, right? I don't know where I would draw that tangent line, and that's a big deal. Or would my tangent line go like this, or would it go like that? I don't have an actual function to the right of -2 that's close to that point to determine what that is. Get rid of those so we don't get confused. Okay, last example, then we'll do one more from the book, and then we'll call it good. So part C, what about at x equals -3? Okay, so let's look at x equals -3. So first off, let me get a different color. F is going to exist at that point. Okay, so at -3, I can come up and I can find a point there, and I could come over and find the y value, so f is going to exist. The limit is also going to exist. As my x values approach -3 from the left, they come up and they hit whatever this y value is here. Let's say that it's 3. So I know that f of 3 is 3, -3, excuse me, is 3. As I approach -3 from the left, okay, then I can see that I actually have a limit there. So my limit exists. And the question now is the limit equal to the function value? Sure enough, it is, because the limit equals 3 and the function value equals 3. So this guy is continuous. However, it is not differentiable. So remember when you saw the definition of differentiability, maybe not the definition, but they gave you examples on page 93 of examples of when you can find a tangent line and when you cannot. So at -3, if you notice, remember the derivative should be a function. So I could draw a bunch of different tangent lines. This is what we call a cusp. And we are not differentiable at cusps or corners. I hope that makes sense. One more example and then we'll be done with 1.5. This one is also from your book. I decided to do this one because I am asking you in your homework to do number 30. And number 30 says for you to do number 29 or do something different with the same thing as 29. I hope that's not too blurry for you, but it's number 29 in your book on page 97 if you need to look at that. So this isn't actually a question really of differentiability and continuity. It is in a general sense, but it's more of an example of how we might set up a function. So let's look at this. So we have the revenue sales. So we have the owner of a photo, well, you can read, of a photocopy store charges 7 cents per copy for the first 100 copies, 4 cents per copy for each one exceeding 100. In addition, there's a setup fee of $2.50 for each photo job. Determine R of X, the revenue from selling X copies. So we have a couple situations here. So let's let X equal the number of copies. It's always good to define your variables, especially when you're doing word problems, okay? So we have two things. We have if if we're less than 100 copies or exceeding 100 copies. So let's consider if X is less than or equal to 100 copies. Let's see what our revenue would be in this case. Then our revenue, right, R of X would equal, there's a setup fee of $2.50. So you are going to pay the $2.50 no matter if you even get one copy or not. Okay, $2.50 just to set this up. Then how much does it charge if we're within less than 100 copies? 7 cents per copy, excuse me, thinking of coffee. 7 cents, so 0.07 cents per copy. So I'm going to take 7 cents times 10 if I have 10 copies, 7 cents times 50 if I have 50 copies, or 7 cents times X if I have X copies. So this is my revenue function, right? $2.50 plus 7 cents per copy. That's my revenue function if I have less than 100 copies. My other question, what if I am greater than 100 copies? I have a different revenue function then, right? Because we give a break to those people that get more than 100 copies. Still charge the $2.50 setup fee, but now we are only going to charge 4 cents per copy. So instead of 0.07, I'm going to have 0.04x. And the whole idea basically of this problem is to get you to set up what we call a piecewise function. So what is R of X? Oh, those are hard to do on this board. I've not been practicing my squiggly lines, as I call them. That is not the technical term for those in mathematics. I call them squiggly lines. Here's what our piecewise function says. My revenue will be the top function. I'm not going to put the dollar signs because maybe we know what we're talking about. Then we just put a little comma here. And we say, here's the requirement, though, on X. It will be that top function as long as X is less than or equal to 100. And it will be the bottom function as long as X is greater than 100. So that's how we're going to describe this revenue function. If you look in your book, you'll see examples of that. I'm sure you already have. And that is our solution for part A. If we look at B, it says if it costs the store owner 3 cents per copy, what is the profit from selling X copies? Remember, revenue is just the total amount of money you bring in. That's not how much money you make, right? It costs you money to make those copies. You have to maintain the copy machine, you have to buy the copy machine, you have to pay your employees, okay? So it costs the owner 3 cents per copy. What is the profit? And then right here it says recall that profit is revenue minus cost. So again, we have this situation where it depends on what we're dealing with here. So if sorry about that. If I look at, let's say X again is less than or equal to 100. I'm going to use a different color. I think that's a little hard to see. So let's say that, I really am. Let's say that X is less than or equal to 100. Then my cost function, just like this says here, profit is revenue minus cost. So that means profit, let's call it P of X, is revenue minus cost. So in this case, what's my revenue? Well, I want to pick this guy here because I'm looking at when am I less than or equal to 100 copies. That'd be 250 plus 0.07. That's the amount of money I'm making on each copy. Then I need to subtract the 3 cents per copy, okay? And I can go ahead and I can combine these two together if I would like. So my final answer here, my cost function, is also going to be a piecewise function where I'm going to put these two together. It'll be 2.5 or 250 minus 0.04 now. If X is, I'm getting a little close here, sorry about that. If X is less than or equal to 100. And then on this one, if I subtract the 0.03x, that's the cost per copy, right? This will give me, and I'm so sorry, that should be a P. You're probably yelling at the TV right now, or TV, until I'm maybe not 18. You're yelling at the YouTube video. This is as if x is greater than 100. Oh, sorry about that. And this again, as you know, you saw that. That should be my profit function. All right, I'm right at 15 minutes and I may have lost you, so that we'll call it good.